start the technical session. Umesh is our first invited speaker, and it's Umesh Vazirani from University of California in Berkeley. It's a great, great pleasure for me to have him here. I've known him for at least 30 years, and he's one of the main figures in the computer science circles in quantum information science. And I was very, very pleased when he moved in the field many years ago, and he's almost set up now, so that I think I don't need to fill up times anymore, and he'll be able to ready to start.
Okay, thanks very much, Gilles, and I'd like to thank the organizers for inviting me here. What I'd like to talk about is joint work with Thomas Wiedig, who I guess, well, until recently he was a postdoc at MIT. Before that he was my PhD student, and I guess he's now moving to Caltech. So okay, so let me start by talking about, well, as Gilles said a little while earlier, there was a momentous event that occurred about 30 years ago, not far from here in Bangalore, where this paper, this famous paper of Charlie Bennett and Gilles Brassard was published. Now, at that time, I don't think the people in Bangalore really knew how momentous it was. In fact, I don't think anybody in the world knew how momentous it was for many, many years afterwards. And as Gilles and Charlie told me, actually maybe Gilles told me that it wasn't. Sorry. It wasn't until 1994 when Charlie and John performed this experiment. Was it 89? Or? Okay, well, 89, and it wasn't until 89 that people started taking notice. Now, what Gilles described to me was that it was sort of interesting. I don't believe you can see it that clearly, but it was a tabletop experiment where Alice sat here and Bob sat there. It was sort of it was doing cryptography over this distance. But the interesting thing that I think Gilles found always extremely amusing was that in order to believe that this was perfectly secure quantum key distribution, you had to plug up your ears, because when a 1 was being transmitted, it drew more it sort of drew more current from the power source, and you could hear this because it hummed a little more loudly. Okay, so but then following this, there were two different tracks on which there was a lot of work that happened. So one was on the theoretical track of actually proving that quantum key distribution was unconditionally secure. So of course there's something. Okay, I don't. All right. So for whatever reason, okay. So so of course the goal of quantum key distribution is for two distant parties, Alice and Bob, to share a common a secret key, which cannot be which is secret from an eavesdropper, and the rules of the game are that Alice and Bob have a quantum channel and a public classical channel. Okay. So the BB84 protocol was in this kind of setting where you prepare the state and measure. Alice prepares the state, transmits to Bob, who measures, and it wasn't until about 15 years later that there was a proof of unconditional security of this protocol by Myers and Shaw and Prestill, and in the process of giving this this proof of unconditional security, one had to they had to use many, many tools, some of which they had to invent, having to do with uncertainty relations, entanglement distillation, and error correcting codes. Okay, so okay, so it's QKD has also been a major field of experimentation. So I'm sure you all know there are dedicated fiber optic networks that have been established. There are experiments on carrying out QKD over free space links by various groups in Europe and Asia and the US. And there are commercially available systems by companies, including Nicolas's company, ID Quantique, and MagicQ. Okay, so in all this, unconditional security is a major point of quantum key distribution. So the fact that you get security based only on the laws of physics and not on unproven assumptions as in classical cryptography. So, but then there's a problem that creeps up, and this problem was already sort of there was a hint of that already in this early experiment where when you were transmitting a 1 versus a 0, you could actually hear the difference. So now in the actual implementations, there've always been these there've been this sequence of hacks where quantum key distribution, after it's been implemented, actually gets broken. And so you could ask, well, how could you break something that's unconditionally secure? Well, so the unconditional security is, that's a mathematical fact. So the protocol is actually secure under the assumption that quantum mechanics, the laws of quantum mechanics hold. The issue is, how is it actually implemented? And so in the actual implementations, it turns out that there are ways that you can attack those implementations. In other words, there are side channels like the noise in the first implementation, but more subtle side channels that have been attacked. And so the issue that one has is, how do you make sure that there are no such side channels? And if you have to do this, if you have to think about these side channels one at a time, then in what sense can one call it unconditional security? Right? So somehow quantum mechanics gives us this scheme which is secure only under the where you only have to assume the correctness of quantum mechanics. I'm sorry. Oh. Okay, but on the other hand, quantum mechanics also makes the implementation of this kind of cryptography very subtle, where now you have different modes of attack that were not available classically. And so back in 1998, Myers and Yao started this program of putting quantum computing on a completely secure footing, without any assumptions on the actual quantum mechanical devices that were used in the cryptographic protocol. Okay, so what was Myers and Yao's idea? So their idea was that you could deal with side channel attacks by using entanglement. So they thought of a scenario where Alice would generate 2 entangled photons, say in a Bell state. And then what she would do is measure the first one and transmit the second one to Bob. Now, what they were relying on was the fact that since these photons are perfectly entangled, right, that if if you could check that these were perfectly entangled by checking that they pass some CHSH-like tests for entanglement, then in fact you could prove that no information leaked through side channels. Okay, so this was sort of a toy model in which they actually proved that if you did some certain CHS-like test, then in fact you could have no further entanglement with any other degrees of freedom, and so you would get, this could be a basis for perfect security. Now, what they also issued was a device-independent quantum key distribution challenge. So what was this challenge? So in this challenge, you assume that your quantum devices are completely untrusted. And so you have no idea what's going on inside there. All you assume is that you can communicate with these devices by inputting, say, zeros and ones, and the devices output 0 and 1. And so what you must do is you can test to see if they, so there's supposed to be some claimed behavior of the devices. But since you don't trust these devices, you're going to have to assume, you're going to have to test them. And so in the protocol, you only believe what you can test. Okay? And so the question was, under these circumstances, can you actually prove that QKD is possible? That Alice and Bob can share a perfectly random key which Eve has no information about. Okay, so now it turns out that there was already a hint of device independence in an earlier protocol by Arthur Ekert, which was based on entanglement. So here's the Arthur Ekert's paper, and in that he talks about, towards the end of the paper, I think this may be the last paragraph or the second last paragraph in the paper, he talks about, well, however, as we want the two particles to be in a pure singlet state, and Alice and Bob test for it through Bell's theorem, then we cannot correlate the third particle with the other two without disturbing the purity of the singlet states. Therefore, I conjecture that there's no universal state of the faked source which will pass the statistical test of the legitimate users on the subsystem of the two correlated particles A and B. So it seems to, it seems to be implicitly talking about something along the lines of what we want, which is device independence. Well, maybe he didn't think, it wasn't completely on his mind, but he was sort of heading there. Now, after the Myers and Yao challenge, in fact, things didn't progress for quite some time because it was actually hard to work with the conditions and with the most general conditions. And then in 2005 there was a lot of movement based on two sets of papers, one by Barrett, Hardy and Kent, and the other by Asin and Nicolas Jessan and his co-authors. And what they did was they gave, they basically showed how to carry out device-independent QKD in a provable way, but in a slightly more, but they had to assume slightly more from the devices. So what they had to assume was, okay, so the devices were, were designed by the adversary, Eve, so they're completely untrusted. They assumed spatial isolation, which of course you have to do, so you have to assume that Eve is not sitting inside Alice or Bob's lab, because otherwise, of course, all bets are off. Of course, you have to assume quantum mechanics, and well, maybe, but the interesting insight was, instead of working with all of quantum mechanics, just work with non-signaling distributions. And then they were able to show that as long as your successive uses of the, as long as the successive uses of the device were completely independent, then you could prove that through some amount of testing of the devices that the protocol actually was perfectly secure. So without assuming anything else about what was going on inside the devices, but you had to assume that either that successive uses were independent, or you could alternatively assume that inside your device were n different boxes, and these n different boxes did not talk to each other, so that there was perfect independence between them. Now, very recently, I guess last year, there were two papers that showed that in principle you could do device-independent quantum key distribution without this independence assumption. So one was by Barrett, Kohlbeck, and Kent, and the other was the paper I talked about yesterday with Reichardt and Falk-Unger on commanding black box systems. But both of these results suffered from a problem, which is that the protocols were very inefficient. They did not tolerate noise, and the rate at which the key was generated tended to 0 as n tends to infinity. So okay. So today I'll talk about a protocol which actually solves the problem without these independence assumptions, and which tolerates a finite amount of noise. I think it tolerates 2% noise, and it generates key at a rate of 5%. So it's it really addresses Myers and Yao's challenge. Okay, so before I can describe the protocol to you, let me just review the CHSH game, just so that we can locate the protocol in terms of that game. So remember that the CHSH game is the following. So you have two players, Alice and Bob. In our case, the two players are going to be the two devices that Alice and Bob have. So we think of the players as D sub A and D sub B. Now, they are given as input random bits, X and Y, and they cannot communicate with each other. And the challenge is, so what Alice and Bob are trying to do is cooperate in outputting A and B bits so that they output the same bit unless the inputs are both 1, X and Y are both 1. Now, you all know that classically it's impossible to do better than 3/4, but quantumly you can achieve cosine squared pi by 8, or 0.85% chance of achieving this condition. And what's interesting for the device independence protocol is actually understanding what this quantum strategy looks like that achieves this 0.85 chance of success. So what the strategy involves actually using a shared Bell state, and then Alice and Bob measure their qubit in one of two bases depending upon the input, X or Y. So on Alice's side, if X equal to 0, then this qubit is measured in the standard basis, and if X equal to 1, it's measured in the pi by 4 rotated basis. And on Bob's side, if Y is 0, it's measured in the pi by 8 rotated basis, and if Y is 1, it's in the minus pi by 8 rotated basis. And this achieves in all 4 cases a success probability of cosine squared pi by 8, and that's this the CHSH inequality. So now, in our protocol for device independence, we are going to add a third input to Alice's device. Okay, so the inputs are going to be 0, 1, 2. The output is still going to be 0, 1. And here's how the game is going to be played, and then I'll describe to you the properties in a couple of minutes. So on Alice's side, on 0, 1, she's going to do exactly as she did before. But if she got input 2, then she pretends to be Bob and pretends that he got as input 1. Okay, so she does exactly what Bob would have done on input 1. She measures in the minus pi by 8 basis. And then Bob does exactly as he would have done otherwise. So now, you see, so if the inputs are 0, 1, then they are just playing the CHSH game. And if Alice gets input 2 and Bob gets input 1, then they are both measuring in the same basis. Now, if you measure a Bell state in the same basis, you get a random bit, but both of them get the same random bit. So whenever this happens, that's a, so what they're doing is this condition 2, 1 is when they actually generate their secret random key. You see, because they're both getting the same random bit as output, right? These other conditions when x is 0 or 1 is when they are testing the CHSH condition. So they are testing for Bell inequality violations. And so it's a combination of these two things that makes the device-independent protocol work. Okay, so this resulting protocol is a very simple variant of Arthur Ekert's 91 protocol. Okay, so A takes as input 0, 1, 2, random, one-third probability. B is a random bit. If they are honest devices, then they actually share Bell states and they measure in the bases that I already pointed out. So now, on these inputs, you're checking the CHSH condition. On these inputs, you're generating the key. Now, of course, this is what the honest device is supposed to do, but we don't trust the device. So what we're going to do, what Alice and Bob will do, is they'll check that the input-output behavior of the device satisfied the CHSH condition on a random subset of their rounds. Okay, so they'll use their public classical channel to pick a random subset of the rounds and then tell each other the results of, what were the inputs, what were the outputs. Now, of course, the eavesdropper, Eve, is privy to all this information. Right? And then the raw key is the output from these rounds, which is then processed as always in a quantum key distribution protocol. Okay. Okay, so this post-processing involves, of course, information reconciliation and privacy amplification, but which involves more communication on this public channel. And so, in order to prove security of this protocol, we have to show that all these classical bits that are exchanged don't compromise the security of the protocol. Okay, but other than that, I don't really, for this talk, I won't really get into the details of this because it's not really important. So all that's important to us is that this amount of information that's passed back and forth did not actually compromise security. Okay, now, so far we've been looking at this view of the protocol from the point of view of honest devices. Now, what we really should be doing to do DIQKD is we have to assume that these are untrusted devices. So this is the picture that we have. We have our two devices. They are black boxes. They share entanglement, and all that we know is, all that Alice and Bob know is that they punch in their inputs. Well, actually, Alice has 3 inputs she can punch in, 0, 1, and 2. There are 3 buttons there. So they punch in their inputs, they see the lights light up, and they perform, they do some simple tests. And at the end of that, they are supposed to take whatever output they got, which is a raw key. They are supposed to, process it, and there should be a proof saying that this is perfectly secure, that the eavesdropper has no advantage in guessing what those bits are. Okay, so what do Alice and Bob actually do? Well, they run the protocol. So they punch in 0, 1, 2 at random, 0, 1 at random, record the outputs, and then what they do is select some linear number of rounds at random, some gamma n rounds for some gamma greater than 0, and share the inputs and outputs for those rounds with each other, just publicly over the public channel. And they verify that for those chosen rounds, when you restrict them to the CHSH rounds, that the CHSH condition is met, that the fraction of rounds in which the CHSH condition is met is at least cosine squared pi by 8 minus eta, where eta is the noise rate that they wish to tolerate. Right? So if it's at least this much, then they'll continue. If it's less than that, then they abort. Right? So what we want to show is that as long as the noise rate is small, then they'll, with high probability, they will not abort, and conditioned on their not aborting, they'll, the protocol is actually secure. Okay, so here's what we actually show about the protocol, that if you can choose your parameters so that the key rate is about 5%, noise rate is 2%, and if you look at the best parameters without even with stronger conditions on the inputs than on the devices, then this is within a factor of 2 of what you can achieve there. Okay, so let's try to think about how we are going to prove that, why should this protocol be secure? Okay, so the reason to believe that it's secure has to do with this property of entanglement called monogamy. Okay, so what you can see is that intuitively, if the devices have to, if they're going to pass these CHSH tests, then they must share Bell states, right? Essentially, that's the only way, okay, so we saw yesterday that the CHSH game has this rigidity property, that if you're going to pass the CHSH test with probability close to cosine squared pi by 8, then the only way you can do that is if if the devices share these Bell states. But on the other hand, if Eve wants to eavesdrop on what's going on, then she must be somehow entangled with the two devices. And so what they must share is not the Bell state, but a GHZ state, some sort of tripartite entangled state. And so monogamy tells us that, in fact, these are incompatible conditions, that that somehow if two qubits are maximally entangled with each other, then they don't have any room to be entangled with any other qubit. Okay, so that's the intuition, but okay, but now in order to prove DIQKD, we have got to actually prove this in a much more general setting. So what's the more general setting? Well, you see, we don't trust these devices. We don't know what's inside them. In particular, their Hilbert spaces could be arbitrarily large. Right? So these are not qubits that are sitting, it's not just qubits. It's an arbitrarily large Hilbert space. And so when we say, well, this device is, has a Bell state with that other one, or it has some amount of entanglement, there's entanglement between this and the other one in order for the protocol to proceed. Well, of course, there are many, many other degrees of freedom, and they could be entangled with Eve. And how do we know they don't help Eve to eavesdrop? So this sort of monogamy of entanglement, the simple bounds on monogamy are not very useful when you're dealing with untrusted devices, right? So if you want to think about it by analogy, it's this form of monogamy where people can actually prove results, it's sort of it's sort of this the kind of monogamy you think about in terms of these how do you call it, these romance novels where where two people are so much in love they have no, they cannot even think about anybody else. But that's not the way the world works. You have thoughts about many other things. So how do you formalize this notion of monogamy in this much, in this more general context? Okay, so now, okay, so first of all, we know that these boxes, even though they are, they share entanglement with each other, they might share entanglement with lots of other things, right? So what we want to prove is not that they cannot be entangled with anything else, including Eve, but that the kinds of correlations that we can produce when we measure these devices, if they satisfy certain conditions, then those correlations, then there are no correlations possible with other devices. Or, okay, so now instead of talking about what's inside the box, we want to talk about what we actually saw, the kinds of behavior we can see. So that's the first thing. The second thing is, okay, so the difficulty here is not only dealing with monogamy in this context of these large numbers of degrees of freedom, but also in the context of a complex protocol. So there are a few difficulties. The first one is the protocol consists of many, many rounds, and Eve is not restricted to attacking each round separately. So she can attack all of the rounds in some sort of a coherent attack on them simultaneously. Moreover, if she wants to break the protocol, she doesn't need to obtain any one of these bits that is output, right? She can obtain the parity of all the bits that are output during all the rounds, or the parity of some of the bits that are output in some of the rounds. And so there's this possibility of these global attacks, which are then hard to, it's much harder to pin down in terms of, how to make a monogamy statement about those. And the third thing that makes it challenging to actually restrict Eve's information is that there's a large amount of classical information that the protocol leaks to Eve during the public discussion phase, right? So Alice and Bob actually talk to each other on a public classical channel in this protocol, and where they talk about many the inputs, outputs of various rounds. And so what we have to show is that despite all this, the security is maintained. Okay, so now there are, if you think about it, there are two different challenges to proving the security of the protocol. The first is to show that the keys that Alice and Bob obtain are random, and the second is to show that Eve has no information about those random strings, right? So Alice and Bob want to share secret random strings, so we've got to show they're random and that they're secret. So now the first of these two challenges is actually, it's known how to deal with it. So in fact, there's this beautiful sequence of results starting with Kolbeck's PhD thesis, which deal with this problem of certifiable randomness expansion. So the setting here is this. So you're given some random number generator. It's a physical random number generator, and you don't trust it. So how would you test that the output is actually random? Okay. So, I mean, classically, it seems crazy to ask the question, right? Because what you want is every n-bit string to be equally likely. And so what does it mean to test your output? So you use the box, you get an n-bit output, say n is 100 or 1,000. And now what can you do? Well, you could sample it a few times, but a few 1,000-bit strings are not going to tell you very much about the distribution. And so you may as well assume you sampled it once. And then what does it mean to look at one string and say that it's random? Right? So the point of I think the point of Kolbeck's in his PhD thesis was that, well, since we can't, since DIQKD is hard, well, at least one can get out of this notion that when you test that a Bell inequality is violated, you actually are testing that the output is actually random. And so if you build a random number generator which consists of two parts which are entangled with each other, and you test for Bell inequality violations, then you in fact you would actually certify that the actual random number that was output by those boxes is truly random. Okay, so certifying randomness is not the problem. So the second part is actually showing that Eve gets no information about, or very little information about the key. So here's the kind of theorem that we want to prove. So what we want to show is, suppose that there's a probability epsilon that the protocol did not abort when executed with these two devices, DA and DB, which we don't trust. Let E be the quantum system held by an eavesdropper. Okay, so this eavesdropper has access to all the classical information that's exchanged by Alice and Bob on the public channel. And let A be the random variable, which is the output of Alice, of Alice's device. Okay, so this is what we hope is a random key, which Alice and Bob share. Okay, so this out by the output, I mean the output on the rounds where the key is generated, the ones where the input was 2 and 1. Okay, so then what we show is that the conditional min-entropy of A with respect to given P and E. So this is the amount of information that Eve has, including her quantum state and the public, and the publicly exchanged information. The entropy of A is still at least some linear function of n minus log n of epsilon. Now, so this quantity here, the min entropy or the smooth min entropy, the epsilon here says it's a smooth min entropy. This is a measure of secrecy which is the correct measure to use in this kind of setting, because it also ensures universal composability, so which means that the keys that you get from this protocol you can now feed into any cryptographic protocol and it still continues to work. So you can, yeah. Yeah, just for convenience. Yeah, just to reduce the number of parameters. Okay, so let me just say very, very quickly what this conditional min entropy is. Well, the min entropy, the classical min entropy is, it's the measure that's used when you talk about classical extractors of randomness. And when you say that the entropy of a source, let's say of n bits, is k, the min entropy is k. What it says is that no string x has probability more than 2 to the minus k. Right? So if you were to say that the min entropy is n, you'd be saying that every string has probability at most 2 to the minus n. And so since there are only 2 to the n strings of length n, that would say that it's a perfectly uniform distribution. And so by bounding from above these probabilities, you're saying how non-uniform this distribution can be. Now, okay, so if you talk about the quantum conditional min entropy with respect to, if you have two subsystems A and B and you have a quantum state rho, and if you say that this conditional min entropy is k, what that means is that there's some state sigma for this second system, such that if you look at 2 to the minus k times the identity on the first subsystem tensor product with row. Sorry about this. Okay, it's the best I could come up with in PowerPoint. Okay. So if you look at 2 to the minus k times the tensor product of identity and sigma, it's at least rho. So if you stare at this for a couple of minutes, you will see that it's in direct analogy with that statement, right? Because I think this statement says that that if you were to scale your distribution down by 2 to the k, right? If you were to multiply it by 2 to the minus k, then it would fit below the uniform distribution, right? So it's the same sort of statement. Okay. Okay. So now the proof of security is actually somewhat involved. So what I'll try to do is give you sort of a 5-10 minute outline of it, and hopefully that'll give you a flavor of the kinds of ideas that go into it. Okay. So so here's our setting. We what we want to do is show that in the presence of an eavesdropper, you get a shared key which is still securely random. Okay, so the oops. Oh, sorry. So the proof of security is actually based on a number of ideas. So the first of these is what's called the quantum reconstruction paradigm. So this is a paradigm that was initially discovered in the context of classical extractors, so randomness extractors. So there's an extensive theory about how you can take an imperfect source of randomness, an adversarial source of randomness about which you make some assumptions about the min-entropy, and you want to take the output and massage it into a form where it's uniformly random or close to uniformly random. Okay, so this quantum, so classical reconstruction paradigm came up in that context, and based on that, there's this whole notion of a quantum reconstruction paradigm, which we actually used in the work on randomness extraction. So what it does is it combines ideas from classical randomness extraction, from list decoding, pretty good measurements. So it's actually there's a lot of a lot of interesting concepts that go into this, and somehow one has to use this to try to bound Eve's information. Now, in addition to the challenges in the randomness certification, in this setting we have to deal with noise, and that creates new challenges. So we'll see how to deal with those. And then there's this very simple sort of concept that we introduced in the context of randomness certification called the guessing game. So basically the outline of the proof is we use this sort of randomness, this quantum reconstruction paradigm, to reduce the n-step protocol to identifying a single step of the protocol where something, where we can derive a contradiction. And within that single step, we use this guessing game to actually derive a contradiction. Okay, so how does all this work? Okay, so the quantum reconstruction paradigm works like this. So let's say we are trying to show that this key that's output by Bob, or that Bob actually generates, that this is secret, that the eavesdropper has very little information about this key. So we assume for contradiction that, in fact, that Eve has a lot of information about this key, meaning that this output does not have large conditional min-entropy, right? Well, then the reconstruction paradigm tells us that there's some advice that Alice could give to Eve which enables Eve to perform a measurement on her state Okay, so she can perform a measurement on her state based on also the public discussion that she heard. And this measurement outcome is going to agree with Bob's output with non-negligible probability. So remember, the key has n bits in it. And so if it was really random, the output, then Eve could only guess it with probability 2 to the minus n. But let's say that this reconstruction paradigm gives her a method of reconstructing the entire key with probability 2 to the 0.1 n. So now this is an extremely fortunate circumstance. And so we're going to show how to use this extremely fortunate circumstance to actually derive a contradiction. I'm sorry? Fortunate for Eve, yes, yes. I'm sorry?
So it is unfortunate, actually.
Oh, okay, sorry, I stand corrected. This is an extremely unfortunate circumstance. And so we'll show that this really unfortunate fact leads to a contradiction, and so order is restored in the world. So, okay, so now how do we use this extremely tiny chance of an unfortunate event occurring to show anything? So the sort of natural idea to use is conditioning. So if something happens with very with small, exponentially small, but still extremely non-negligible probability, then the way you amplify that is by conditioning on past events. And so what we would do is we condition on past events and say, suppose that what Eve does is this measurement, and then she looks to see if the first so many rounds, on the first so many rounds, she actually was able to predict the right answer, that she was able to predict what this key was. Then she's going to say, okay, now what's the chance, given that this occurred, that I can also predict the next bit of output? Well, that's going to be pretty high. Okay, so there's going to be some round. If this conditional probability is like 2 to the 0.1 n, then maybe after 0.1 n rounds, she's going to have a pretty good chance of being able to predict the next bit if she already predicted the first 0.1 n bits. Okay, so somewhere down the line there's a good place for her to predict, and so we'll focus our attention only on that round. Okay, then we'll also use the fact that the CHSH condition held on average on most rounds, and so we'll now argue that there must be some round on which both of these things happen. That conditioned on all the previous rounds, this round the CHSH condition holds, and also Eve can predict Bob's bit. And now we'll show that this violates the no signaling principle. And to show that it violates the no signaling principle, we'll have Alice and Eve play a guessing game with Bob. So the guessing game is pretty stupid. Okay, it's a little bit like the CHSH game, but a pretty stupid version of it. So the game is like this. Bob is given a random input, random bit as input. Alice and Bob cannot communicate with each other. They share entanglement. I guess Alice Eve versus Bob cannot communicate with each other. They share entanglement. And now what these two are asked to do is guess why. Okay, so it's obvious. They cannot guess with probability more than 50%. In fact, they cannot even guess with probability less than 50%. Because it's a completely random bit, so there's nothing they can do. No matter what they guess, it's 50-50. Right? And so now what they do is, what they do is they simulate the protocol. Okay, so what they do is the following. So remember, this was part of a larger protocol. So they run their protocol, the DIQKD protocol, up until the point where, so they keep running it over and over again. Each time Eve tries to guess Bob's output, and then assuming that she guessed correctly on the first so many bits, they stop the protocol there, and then they now focus on the next round of the protocol, right? Where we said these nice conditions hold. And that's where they play this guessing game. And now, what Alice does is she pretends to play the next round of the protocol, except with input x equal to 2. And she looks at what her output is. Now, what she knows is, at this point, if Bob's input was 1, he got the same output, right? But on the other hand, Eve also has a guess for Bob's output. So if these two match, then they guess Bob's input was a 1. If they don't match, they guess it was a 0. And you can show that this gives them an advantage a little bit over half. Okay? And so this is how you contradict the guessing game. Oh, sorry, this is how you contradict this, reach this contradiction that Eve could not possibly have so much information about Bob. Now of course, in order to use the reconstruction paradigm, what we had to do was Eve had to get this short amount of advice string. You know, she had to get some amount of advice, which was some small fraction of n, say 0.0001 n. But she can just guess that. If she can guess 0.0001 bits, n bits, and then reconstruct 0.1 n bits of Bob's key, that's already a contradiction. Okay, so that's how this thing is played. Now, unfortunately, this is not the end of the story because there's something that still goes wrong with the reasoning that I described, because remember what we did is we started by assuming for contradiction that Eve had a non-negligible, you know, that there wasn't a lot of the conditional min-entropy of this output given Eve's information was not very large. But then we used conditioning, you know, so we said Eve can guess this string with probability 2 to the minus 0.1 n, and then we amplified that probability by using conditioning on previous rounds to show that there's some round on which there's a high chance of success. Eve has a high chance of guessing correctly. The problem is, once you condition like this, and you're conditioning a lot, now you may have changed the distribution on Bob's input. You know, if you conditioned on what you're conditioning on a lot of things, right? You're conditioning on public discussion, you're conditioning on this measurement. Who knows what happened to the distribution? So, and of course, if Bob's distribution changed, then the fact that Alice can guess it, you know, guess Bob's input, that's not very meaningful because it wasn't uniformly 0 or 1. So the solution is to show that, in fact, this conditioning cannot really change the distribution on Bob's input. And to do this, we play another guessing game. So this time it's a guessing game where we show that if the conditioning changes its distribution, then Alice and Eve can signal to Bob without communication, right? Because in, you know, if the distribution changed here, then you know, and they okay. So to make this precise, you really have to use the quantum Pinsker inequality, but it all works out. Okay, so that's you know, that's sort of a high-level overview of the argument. Okay, so let me conclude by a few thoughts. So first of all, you know, it would be interesting to see how to use this kind of argument further to you know, there are various situations where you'd like to use classical testing of untrusted quantum devices to achieve certain results. And so this gives, you know, this gave us some technique for doing it, and it would be interesting to see where else one can use these techniques. As far as the actual bounds go, the bounds that we achieved, we didn't really work that hard on optimizing the parameters. So it's quite possible. So these are within a factor of 2 of the, you know, the best bounds known, even without achieving fully device independence. but it's possible that by playing with the parameters in the protocol in an interesting way, you can actually improve these bounds significantly. So we haven't really gone through that exercise yet. The other interesting thing about all this is what it says about monogamy of entanglement. So monogamy of entanglement is really it's a pervasive feature in quantum mechanics. So it's used, of course, in this context, but it also shows up, for example, in various phenomena in quantum systems, such as, for example, area laws for many-body quantum systems. So the main intuition for the area law is entanglement, is monogamy, right? That your local operators, they can entangle your particles locally, but then once they entangle these if they're able to entangle locally these particles a lot, then somehow you can't also entangle them far away, and so you can't carry the entanglement around. So that's the intuition, but then how do you actually formalize it? This gets very, very difficult. And so this whole issue of being able to formalize in a general context quantitative bounds on monogamy, this has been a really fundamental open question in quantum information, and you could view what the bounds we got here as a first step towards developing such a theory of quantitative bounds for monogamy. And so it would be interesting to study these much more generally and see how generally can one establish these quantitative bounds. Now the other thing here is what we were able to do in this context was actually deal with errors. And there are other protocols, for example, actually the randomness certification protocols, where we don't know how to deal with errors. And it's quite possible that these ideas can be used to actually make those protocols robust as well. Okay, so thank you for your attention.
I will abuse my position and ask the first question. Of course, all of this device-independent theory, if you want to implement it, requires that you can withstand or circumvent the detection loophole. So for any of this thing to be secure, really, you need apparatus that has a very good detection. So I'm not asking the right person, but how much do you think that this, I mean, if you look at the earlier proposals for device independent, they were completely impractical because they needed these very, very long laboratories, no communication between many devices. Whereas this is, when you look at it, it seems completely reasonable. But it's only reasonable if you can do it right. And so after this introduction, let me now ask you a question which is probably not, you're the right person to answer this, but how reasonable you think this is that it would ever be implemented?
Yeah, so in terms of the detection loophole, my understanding is that but there are probably experts here about this, but my understanding is that the race is very much on to do loophole-free Bell inequality tests, and maybe the experiments have already been done, and those who are only just about to carry out the experiments might even be a little too late in the race. So that's my current understanding of it, but maybe somebody else can address that.
But of course you need a detection-free loophole with photons if you want.
Yeah. So maybe yeah.
Nicolas.
Yeah. So I have a question, but before maybe just to having a practical device-independent QKD. Now, my question to you, Umesh, is what resource are we actually using when we do this quantum, not this device-independent quantum key distribution? Is it non-locality? Is it entanglement? And actually, it seems to me that we are using none of them, or that we don't really understand which resource we use. And the reason I have doubts about the resource we use is that the noise tolerance of any of these protocols, even those that only address individual attacks, are always far away from the threshold to violate the Bell inequality.
Yeah, so sorry, you know, this may or may not address your question. Maybe you can tell me if it does, but I should say something that, you know, for these results, we actually, you know, these are, so our, you know, we are actually using a quantum reconstruction paradigm in the proof, which means we are going beyond the no signaling bound. You know, so in terms of resources, it's you know, in fact, there's a recent result by Tashma and somebody's showing that if you were just trying to use no signaling arguments, then in fact you cannot possibly prove security of device QKD. So you cannot even do simpler cryptographic tasks in that model. So somehow it was really essential here that in addition to no signaling, we were actually making use of more constraints that quantum mechanics gives us. So that's an essential part of the proof, and the reason we know it's essential is because in its absence, it was recently shown that you cannot possibly establish security.
Which one are we using?
I'm sorry?
So which additional assumptions?
So well, you know, I mean, this is so okay. That the point is that there are a lot of ingredients that go into it, and hopefully, you know, one of the things hopefully that will be done is to simplify these proofs, because right now, you know, they are working pretty hard to get these. So it would, as you said, it would be nice for two reasons to simplify these. One is mathematically, it would be nice to know, well, you know, that they are, you know, so right now, you know, what do? You have to go through these particular quantum extractors, but then those use list decoding, and to do the list decoding, you need pretty good measurements, and you know, it's really a big pyramid that's built up here, and so one would like to simplify that both mathematically, but also, as you said, to understand the physics better, to understand exactly what are the minimal conditions that'll give us this.
Yes.
Charlie, next question.
Yes. In the many steps that you gave there, what I didn't quite see was where the protocol protects against the untrusted devices remembering the outcomes from previous rounds and multiplexing it into their behavior in subsequent rounds. This must have been taken care of by these various bounds and list decoding and so on that you did, and the extraction, but I didn't exactly see where that was defeated. And the other question related to that is, I guess you need these devices, as they're untrusted, they also have to not be able to listen to what's going on in Alice's and Bob's laboratory around them. Because then they could actually learn the key and multiplex that into their output.
Oh no, the key itself is something that they are. You know, let's pretend for the moment that there are no errors and there's no privacy amplification and so on. Then, in fact, the key is exactly what these devices output, right? So on the 2-1 rounds, the output of the devices is exactly the key. So in fact, if they listened and heard back the key, this is information that they knew to begin with. So, so on your first question, where does, you know, where are we preventing, you know, where does this take into account that the device can, you know, the devices have memory? So you know, this is why the argument takes on this structure where what we are saying is, in fact, you know, so our assumption about the device is that it just does something, right? It, you know, and there's no independence between rounds, and then we say, look, what we know is that based on, you know, that if Eve were able to reconstruct, you know, so if the output is not very random, okay, so why do we know the output should be random? Because it violates Bell inequalities, right? So that's why we believe it should be random. But let's say that it was not, and let's say that Eve was able to, you know, then if it was not that random looking to Eve, then we know through this reconstruction paradigm that she can actually reconstruct the entire output, just occasionally, you know, with very, very tiny probability, exponentially small, but you know, so it's exponentially larger than 2 to the minus n, right? It's 2 to the minus 0.1 n. Now that's the entire output that she's reconstructing, and the output, you know, we've assumed nothing about it. We've assumed nothing about how much communication went into constructing this output. But now that we know this, we are conditioning on past steps, and we are saying, just by conditional probability alone, we can say that if she reconstructed this class, now everything is classical. She's reconstructing this classical output distribution with some probability, and now we're saying there must be some history. You know, there must be some point in this protocol such that if she guessed correctly so far, then her chance of guessing correctly in the next bit is very, very high. And now we are focusing on that round, conditional on the past, and we are saying, in that particular round, no matter what was communicated, at least we can count on this. And that's where we are making use of the fact that we reduce from many rounds to one round, and therefore we made our way around all the communication.
We have to stop here. So very quick last question, because you raised your hand a while ago.
Okay, I have a question about the relation between measurement device independent QKD and this device independent QKD. I find that many...
I'm sorry, so what were the two things?
Measurement device independent.
I'm afraid you'd have to explain to me what the first one is.
And I'm afraid there's no time for that.
Okay,
Sorry.
then that's
but
fine.
you can discuss it in private.
Okay, we can discuss offline. Thank you.
All right. So let's thank the speaker again, and don't leave immediately. Now, before we leave, two things. One, remind you to sign up for the excursion, but it's my pleasure to give our speaker a chal.